Okay everybody, we are today looking at how we can work out derivatives of circular functions. Now, very importantly, this is essential, when we are finding derivatives of circular functions, the angle must be measured in radians. This means that if you're using your CAS calculator, the mode must be in radians, and if you've got a derivative given in degrees, with an angle in degrees, you must first start by converting it to radians. I'll do an example of one of those a little bit later on for you. So in general, the general rules, and once again these are on the formula sheet, and once again if you would like to see where they come from, you can look in the textbook for the proofs. However, you'd not be expected to know how to prove these rules. So the derivative of sine of x is cos of x. If we differentiate our sine function, we get the cos function. Remember to always write the argument, the x, in brackets like so. The derivative of cos x is negative sine x, and this is where it's useful to look at the formula to make sure that you do get that negative value there. The derivative of tan x is something called sec squared x. Now many of you might not have met sec squared x before. Sec of x is something that's much more commonly used in specialist mathematics, but sec means 1 over cos, so therefore sec squared x means that it's equal to 1 over cos squared x, and you can give answers either in terms of sec or in terms of cos. We can look at this more generally if we have a value of k. So if we are differentiating and we have a larger function here, we just differentiate the argument as well. The derivative of kx is k, the derivative of sine of kx is cos kx. Derivative of cos of x, the derivative of kx is k, derivative of cos x is negative sine of kx. And derivative of kx is k, derivative of tan of kx is sec squared kx. And once again, sec squared is the same as saying 1 over cos. So let's actually look at some examples and work through these together. But before we do that, we can talk about a few other rules that could be useful. So there are some other circular function identities that can be useful. These are not things that you would be in any way expected to remember for the Tech pre-exam, but they are worth having written down for the Tech Active. Probably you will not need them, but they are useful things to use. First of all, we should remember that if I was to add sine squared x plus cos squared x, that equals 1. Where this comes from, if we have a unit circle, which we've obviously dealt with a few times before, you hopefully remember that if we were to draw a triangle within this unit circle, the radius is 1 of our circle, the x value is given by cos of x, and our y value by sine of x. By Pythagoras, if we've got a right angle here, so what we get is sine squared x, so we square the two shorter sides, sine squared x plus cos squared x equals the square of the hypotenuse, 1 squared, which is 1. This is where this identity comes from. Some other useful identities are called the double angle formulas. These are much more common in specialist maths. Then it's really unlikely that you would need them in methods, so I don't want to spend much time, but I do just want you to write them down and have a list there in a just-in-case type of situation. So the cos double angle formula says that if I have two lots of a particular angle, twice the size of it, that is actually the same as having cos squared of the single amount of that angle minus sine squared of that angle. And we can rewrite this using the rule given earlier, we can rewrite this in a few different ways. It's also equal to cos squared u minus 1, and it's also equal to 1 minus 2 sine squared u. Like I said, these aren't things for you to worry about, just things for you to have written down. We have a sine double angle formula as well, which is equal to 2 sine of the single angle multiplied by cos of the single angle. Okay, what we're going to do now is that we are going to do some examples. To start with, we are differentiating y equals sine of 5x. So we're finding the derivative, dy dx. We differentiate the argument here. The derivative of 5x is 5. And the derivative of sine is cos of the argument staying the same, which is 5x. Remember, these derivatives are on the formula sheet, which will help you to work them out. For the second one, we're differentiating cos of a function here. So what we do is we differentiate the inside function, the argument there. The derivative of x squared is 2x. The derivative of 3x is 3. And we multiply all of that by the derivative of cos is sine of the argument x squared plus 3x. But we also need to remember that the derivative of cos is negative sine, so I'll put the negative out the front here. If I was to have placed the negative in between here, it can be tricky because it looks like we're subtracting, which is not the case. So we tend not to put the negative in that position, so I'll just get rid of that. Now this is actually our final answer. There is no need to go further, there is no need to expand. What we essentially did here, some of you may have realised, was to use the chain rule. Because if I defined the inside function u as being x squared plus 3x, that means that y would equal cos of, instead of x squared plus 3x, we get cos of u. Differentiating du dx, I differentiate x squared to give 2x, I differentiate 3x to get 3. The derivative dy du, derivative of cos of u is negative sine of u, as according to our formula sheet. So therefore, the chain rule dy dx is equal to dy du dx. dy du is negative sine u multiplied by du dx. Remember, we want the whole function, we put it in brackets, and instead of u we can substitute in our u that was defined earlier. And you'll notice that this is the same answer as what we achieved before. It is entirely up to you which method you prefer to use. Personally, I think using the chain rule is quite time consuming in this case. However, you are welcome to work it. So we're now differentiating tan. Same idea as what we were doing before. When we work out our derivative, our original was in terms of f of x, so our derivative now we will use the notation f dash of x. We differentiate the argument, the derivative of 4x cubed, multiply by the power. 3 times 4 is 12. X, subtract 1 from the power gives us 2. And that's multiplied by the derivative of tan is sec squared, and the argument stays the same. Sorry. And this is it. We can either leave it like that, and that is a perfectly acceptable answer, or we can write sec is the same as 1 over cos, so it could be written as 12x squared over cos squared of 4x cubed. Both answers are perfectly fine. Finally, g of x. Now you might notice the difference here is that we've got this degrees sign here, x degrees. Remember what I said earlier, we must write, any angles in degrees must be written as radians. Hopefully we all remember that 180 degrees is equal to pi. If I want to know what 1 degree is equal to, I need to divide both sides by 180. So what I would get is that 1 degree equals pi over 180. Therefore, in order to transform this function, if it's in degrees now, for x, I need to multiply that angle in degrees by pi over 180. That's the same as saying sine of 4 divided by 180. That can cancel out, and we will get pi x over 45. Now I differentiate g dash x. Remember, when we differentiate, we must show that we differentiate by using this appropriate notation. The derivative of the inside function, well, the derivative of pi over 45 times x is just pi over 45. Derivative of sine gives us cos, and our argument pi x on 45 remains. We can leave our answer like this, where the angle, the x, is in radians, or if we like, we can convert our angle here, the argument, back to degrees, and to convert it back to degrees we would have to be doing the opposite. We would have to be multiplying by 180 over pi. If we convert back to degrees, we do need to make sure that our angle we write in brackets here, that now that x is back in degrees, that we put the degrees sign to indicate that that is the case. Now, just to reiterate, both of those answers are fine. We can leave our answer in, well, this format's a bit gross, but either in radians format here or in degrees. But if we write it with degrees, we must include the degrees symbol. Our last answer for today, we want to find the y value and the value of the tangent, or what we really should be saying here is the value of the gradient of the tangent at x equals pi on 3 for a particular curve. So let's just work out the y value first. That means that I'm substituting pi over 3 into my function. I would get cos squared of 2 times pi over 3. When we say cos squared here, what that means, another way of writing this, and we have 2 pi over 3 here, is that I am squaring this whole answer. We think back to what we did earlier on with our exact angle values. 2 pi over 3, which quadrant will we be in? Well, as we're moving around our quadrant, we get to pi over 2 here and pi here, therefore we are in the second quadrant. In the second quadrant, sine is negative. So this is the same as the value of negative cos of pi on 3. And we're going to square this answer. Cos of pi on 3, I've mentioned a few times before, you must know your exact angle values. And cos of pi on 3 is equal to a half. We square this answer, negative a half times negative a half gives me 1 over 4. Now for the second part that we're looking at, we want to find the value of the gradient. So if our original function is h of x equals cos squared. Now I'm again going to write cos squared like this to show that it's the outside function, because we need to use the chain rule once again. So using the chain rule, we differentiate the outside function. So let me just make this a bit colourful to hopefully make it a bit clearer. The outside function is this part here, the squared part. What we do is we multiply by the power and we subtract 1 from the power. We leave whatever was inside exactly as is. But we need to multiply this by the derivative of the inside. The derivative of the inside function, when we differentiate cos of 2x, derivative of 2x is 2, derivative of cos is negative sine of the argument. Now it's not nice to write this negative in this position here in between because it looks like a subtraction, 2 times negative 2 is equal to negative 4, and we get cos of 2x multiplied by sine of 2x. At this point, we could, if we liked, use some of those double angle formulas from earlier to rewrite this expression, but I think that's just making things much more difficult than it needs to be. Instead, we're wanting to find the gradient of the tangent at this point, so let's now substitute in our value of pi on 3. So we will get negative 4 lots of cos of 2 pi on 3 multiplied by sine of 2 pi on 3. Luckily for us, we figured out earlier, so we have negative 4 times, we figured out earlier that cos of 2 pi on 3 was equal to negative 1/2, so it's going to be the same value. Sine of 2 pi on 3, we do need to calculate this. Let's look in our unit circle. We need a unit circle again, so here we go. Our unit circle. 2 pi on 3, like we established earlier, is here in the second quadrant where sine is positive. So it is the same as the value of positive sine of pi on 3. Exact angle values are something that you should know. So we get negative 4 times negative 1/2 times the sine of pi on 3 is the same as root 3 on 2. This cancels out to give us negative times negative is positive. 4 multiplied by half and another over 2 there, we just get the answer of square root of 3. Please be careful, you're putting functions together. You do need to use the chain rule. We need to use a whole lot of rules and put everything we know about calculus all together. That's all for today. If you have any questions, please make sure you write them down and ask me next time we have class.